So I'm very excited on behalf of the IDE to welcome everyone to another IDE lunch seminar. Today, we are delighted to host Professor Hamsa Bastani, who is an associate professor of operations, information decisions, as well as statistics and data science at Wharton, where she co-directs the Wharton Healthcare Analytics Lab. So Hamsa's research primarily focuses on developing novel machine learning algorithms for dynamic learning and optimization for social good. And putting this into practice, she's worked closely with several national governments, including Greece and Sierra Leone, to deploy algorithms at the country scale to improve public health outcomes. Today, as you can see, we're going to be hearing about how we should rethink fairness in human AI collaboration and really think about kind of compliance and the human angle. And so without further ado, please take it away, Hamza.
Thanks so much for the kind introduction, Mohammed. It's a pleasure to be here. And like Carrie mentioned, please unmute and ask clarifying questions as we go along. I'd love to keep this as interactive as possible. This is some work I've been doing with Hamsa Ge, who is a data scientist who is part of the Wharton Healthcare Analytics Lab, and Bastani, who's a faculty at Penn CIS, about how we should be thinking about fairness when we're dealing with human AI collaboration, what that means for how we design our algorithmic advice tools, and so on. And before I get started, I always wanted to say a little bit about why I think human AI collaboration is important, because I think usually the perception has been that as algorithms are getting more and more powerful, we don't really need to involve the human element as much. So I wanted to give two examples from like my experience where I think this has actually been critical. So the first one, like Mohammed mentioned, we had the great opportunity, along with Kimo Andrakopoulos and Vishal Gupta, USC, to work with the Greek government on their targeted COVID-19 testing platform. So essentially, Greece faced a very, very strong resource constraint when COVID hit. They were getting 30 to 100,000 daily tourist arrivals, and they wanted to make sure that they were protecting population health by screening these arrivals to make sure that anyone who tested positive was actually getting quarantined rather than going and partying on beaches and in nightclubs and actually spreading the infection throughout the country. But unfortunately, at that time, they were only able to test about 6,000 to 8,000 people a day because they had a very strong PCR testing supply chain constraint. So this is a classic resource allocation problem, exactly the kind that we usually work on. We're thinking about allocating a limited subset of tests to a large population in a way that was going to maximize some objective. In this case, identifies the most COVID cases. So we used a reinforcement learning algorithm to do this. The paper actually came out in Nature a couple of years ago. I won't go into details about it, but this is exactly the kind of tool where we think like, oh, we used a very powerful algorithm and it worked well. And so you wouldn't really think that the human element here is super critical. But actually, it turned out that it was. So throughout the summer, we created a bunch of dashboards that public health policymakers could look at to see what was actually going on under the hood for the algorithm. And what we found was that in the middle of the summer, there was one particular passenger type that was low risk for most of the summer, and then suddenly in one day shot up in estimated risk. And so naturally, the reinforcement learning algorithm is kind of responding to the risk estimates that it collects from the data. I mean, it's not, conscious or anything. So it basically was allocating a whole bunch of tests, and it was, creating a lot of risk estimates for this particular population. Because we had these dashboards that kind of tried to communicate in an interpretable way what was going on, it was immediately flagged by policymakers because they were like, we've seen no other evidence on the ground. We've seen no other evidence from other epidemiologists that this particular type is high risk. Like what's changed, right? And so we were able to look in the data, and we quickly identified that one of the labs that was doing the COVID testing incorrectly submitted 8 copies of the same positive test. Everything's de-identified, so it's not easy to like figure out that this is the same person unless you actually start an investigative process here. And so instead of seeing that there was one positive label, we were seeing 8 positive labels, which obviously is very different from a machine learning or data perspective, right? So again, this is a fully automated system, but at the end of the day, the system is only as good, the algorithm is only as good as the data you feed it. And so the human element can be pretty critical to like debug these kinds of data flow issues or inconsistencies that naturally happen in any real world process. Another example is like some work we've been doing with the Sierra Leone government recently, where we are using an algorithmic allocation tool to distribute essential medicines throughout health facilities across the country. We use this decision-aware machine learning algorithm that actually reduces unmet patient demand by about 20% by better matching the supply of medicines that we have to the demand across the country. And again, this is something that looks like a fully automated system. It's supported by a dashboard. And again, we find that often the algorithm can't really achieve full capacity because there are lots of things that go wrong on the ground. So in Sierra Leone, you often have flooded or unusable roads. There might be trucks or drivers who didn't show up or missing that day. And so you can't actually operationalize the allocation that the algorithm is telling you to operationalize because, there are a lot of these real world constraints that materialized at the final point, right? And so you actually need pharmaceutical managers or non-technical decision makers to modify these algorithms, algorithmic predictions to accommodate, on the ground realities. And so we see this as like a consistent pattern that like any successful algorithmic tool has to interact well or interface well with human decision makers in order to actually achieve the intended impact. If not, you're going to run into issues where we either have inefficiencies because of some sort of system failure that the algorithm was not trained to recognize, and we don't have historical data to even train it to recognize it, right? These are all like one-off issues that kind of happen. So there are obviously many others. This is just a couple examples from my experience, but like, as we know, like we have algorithmic support tools that help judges make bail decisions. So ultimately the judge, the human decision maker, makes the decision, but it's supported by an algorithmic risk assessment tool. In the medical field, we have radiologists making diagnoses based on algorithmic risk advice, health risk prediction, feedback interventions for physicians. There's just so many of these that have become a part of our decision-making process. In any field where decisions are hard and noisy, and you want to account for, complex and rich features when you're making the choice, right? Any questions at this point? Great. So obviously, as soon as you have an algorithmic element that is going to inform actual decisions that affect real people in high-stakes settings, there are a lot of concerns about fairness. This is a huge literature, so I'm not going to do it justice in any way. But for those who might be unfamiliar, I just wanted to quickly bring up a couple examples that are popular in the literature. For example, with FICO credit scores, they found that Black non-defaulters are much less likely to qualify for loans than white non-defaulters. For health risk prediction, there's an excellent science paper about how Black patients are much sicker than white patients with the same risk score. Criminal recidivism, and so on. So in all of these cases, we often find that algorithms are not uniformly fair or equal at predicting across different protected subgroups. And that can cause disparities that can cause, further long-term consequences. And so there's been a big algorithmic fairness literature that has kind of emerged in the machine learning community and as well as other communities about how we can actually train these machine learning algorithms in a way that they ensure fairness in isolation. So if I'm building a predictive algorithm, instead of just minimizing my loss, I'm going to usually typically enforce some sort of constraint that says that my algorithm should satisfy, demographic parity, equality of opportunity, and there's like a whole wealth of definitions that you might want to pick in a context-specific way. And depending on the kind of machine learning algorithm, there's also like a whole host of different methods, right? But I'm not going to try to summarize this, but the guarantees typically are of the form that if this algorithm makes predictions or decisions that are approximately fair, given the subgroups that you've identified with high probability. So it's similar for men and women, or it's similar across races and so on, right? But what actually happens in practice is that, so let me give you an example. So some of these tools have been deployed for improving radiologist accuracy or to make judge sentencing fairer. And what we've seen is that in a lot of case studies, this has actually backfired, and these algorithms haven't actually improved fairness, even though they were designed to be algorithmically fair using this kind of mathematical formulation. And we think that the issue really is that these algorithms are trained to be fair in isolation, but they're being deployed in a human AI collaboration. And humans aren't perfectly predictable. They decide when to comply with the algorithmic prediction and when not to comply. And that completely changes the fairness implications of an algorithm compared to when it's operating alone. Right. So for instance, imagine you have this toy picture where the algorithm decides that this person probably doesn't need a procedure, and the doctor agrees and doesn't give them a procedure. So in this case, they complied with the prediction. And then in the next case where you see an African American, like, or a minority patient, and the algorithm is fair, and so it kind of says, okay, this person also doesn't need a procedure, but the doctor actually does offer them the procedures, and the final decision becomes unfair, right? Because the human is basically deciding when they want to comply with the algorithmic prescription and when they don't want to comply with the algorithmic prescription. And that actually creates distortions in outcomes that are fair versus unfair. So let me go back to the example about the radiology paper. So this was a paper by Agarwal et al. And they basically found that AI models were substantially more accurate than radiologists to begin with. So the issue is not that these algorithms are actually not valuable or not predictive, but access to the algorithmic assistant didn't improve diagnostic quality on average. So it improved quality for some subgroups, and it hurt quality for other subgroups, which is typically what we think of as creating unfairness. And the issue they found is that humans, it's not like they're trying to create unfair decisions. They have a set of information that they're considering. The algorithm is offering them a separate set of information. Those might be correlated in complex ways, and it's very, very difficult to think about how to actually do this Bayesian updating so that you create a decision that's equally optimal for all subgroups, right? And so selective compliance was actually driving some of these issues. Similarly, if we look at the sentencing data, there was a similar challenge in that there was no benefit. They found that there was no benefit in safety or incarceration by deploying this algorithmic decision support tool that was intended to make Virginia judges fair. In fact, racial disparities actually seem to increase in courts where the algorithm was used more. So this is very surprising because the algorithm was trained to be fair, and yet it was actually seeming to increase disparities in places where it was being used more. And again, selective compliance seemed to be a key issue here. And there are a lot of challenges, right? Like, for example, in a high-stakes setting like this, the algorithm is designed to just predict who's going to recidivate, whereas judges have a more socially optimal kind of objective. So it's not even the same objective, which is partly why we want to have humans and algorithms collaborate and humans override these algorithms as necessary. But basically, they found that judges typically, one source of bias is that they're more lenient towards younger defendants because they want to give them the opportunity to course correct and become a productive member of society. Whereas the algorithm is sort of not aware of that social objective and is just trying to predict recidivism. So an algorithm might be much harsher to a younger defendant, and then the judge may override that to give them a more lenient sentence. But when they do that, sometimes they might do it more for white defendants than for Black defendants because there's correlations with other kind of attributes, right? And that's basically what happened. That was one of the mechanisms that happened here. Judges were more likely to sentence leniently for white defendants that had a high risk score than for Black defendants with the same score. So even though the algorithmic prediction was technically fair, the way in which the humans operationalized that algorithmic recommendation when they decided to override it versus accept it actually created even more unfair outcomes than without the algorithm itself. And that's really kind of the main challenge that we're going to be looking at. Are there any questions or comments about this? Great. So to revisit the related literature, again, like I said, there's a huge literature on algorithmic fairness, but there's surprisingly little work dealing with how the fairness outcomes are distorted when they're, included in a human AI collaboration where the human is actually selectively compliant. And if you think about it, I can't actually think of many settings where the human is perfectly complying with the algorithm or never complying with the algorithm, because that's not even the point of human AI collaboration, right? We want humans to actually override the algorithm when they think that it's inappropriate or incorrect or there's something else going on. And so selective compliance, I would argue, is always a fundamental tenet of human AI collaboration, and something we should definitely consider if we're thinking about embedding these algorithms into decision making. We should really be thinking about the end-to-end fairness, right? We offer an algorithm, the human intervenes, and then we have an outcome, but we care about fairness of that final outcome. So there has been some work by McGill-Vass and Gillis et al. Showing that selective compliance can cause unfair end-to-end outcomes because of this improper Bayesian updating. But the question really becomes, what do we do, right? So these algorithms, they don't come out of nowhere. We designed them, right? Especially you guys are at MIT. A lot of them are designed by you. So what can we do to basically ensure that these algorithms are, creating the kind of positive impact and not decreasing fairness the way that we'd like it to, right? So from here, I'm gonna start adding some notation and make it a little bit technical, but feel free to jump in and ask any questions. So we're gonna consider a pretty simple decision-making problem. So we have a finite number of types. Let's say that there's k different types of individuals, right? So we've discretized people's features based on what we're observing. This is just for technical convenience. And then we have a binary indicator of a protected attribute. So this could be like race. So in the examples I mentioned, it was Black versus white defendants. It could be gender or whatever. And then we have a binary decision. So typically the decision is binary, where we're deciding, should we treat the patient? Should we give them a loan? Should we give them bail? And so on, right? So those are the primitives. And then we're thinking about designing a decision-making policy that takes into account the features or the attributes of this individual, their protected attributes, so their race or gender, whatever we care about, and maps that to the probability of a decision of y equals 1, right? So whether or not they get this intervention. So for convenience, I'm just going to think that the intervention is a good thing, like, you're getting bail or you're getting the loan, it's something you want. And so I would model my decision-making process for a policy pi. The decision is going to be a Bernoulli random variable of pi of x comma a. So it's random just to account for natural variation in people's decisions, right? So not everyone will choose the same thing given the same data. So we're going to form some probability here. So pi is a probability. So I'm going to define a couple different policies, because in human AI collaboration, there are a couple different ingredients. So one is the human policy pi h that was used by humans in the absence of any algorithmic advice. So for example, with the court sentencing, it would be how Virginia judges were sentencing individuals before they had any kind of algorithmic tool. So this is typically something, at least in this ancient time, that's easy to estimate using historical data. Because in many settings, we actually have been collecting data on what these individuals have been doing before we actually deployed some sort of algorithmic support system for them. In fact, we usually use that data to train that algorithmic support tool. So we can reasonably estimate pi h from historical data that might be available from that time period. And next we have an AI policy. So this is known, pi a is whatever algorithmic recommendation that we are designing and offering to support the human decision-making strategy. And then the next one I'm going to define, so this is the one that might be new, is a compliance function. So this is a mapping that basically takes the individual features and the protected attributes to a 0-1 label, indicating whether the human is going to comply with the algorithmic recommendation or not for that particular individual. So note that whether or not I comply depends on who I'm looking at, right? What their race might be. And it implicitly can also depend on the algorithmic prediction itself. So I'll talk about that in a little bit. But we're basically going to try to be robust with this class of compliance functions. Why? Because the human policy is something I can estimate from historical data. The algorithmic policy is something I know because I designed it and made it up, or whoever was the algorithmic designer made it up. But the compliance function is something that you really have no way of knowing, right? So until you deploy your algorithmic tool, you don't get to see when the human decides to comply with the algorithm and when they don't. And often, even if you see it, you'll only see it for the particular set of predictions, like for this particular policy. If I were to change the policy, I still cannot predict how the human is going to deviate in terms of compliance, right? So this compliance function, we're going to think of it in a very general way and think about things, think that there is no way of knowing this whole class, and we're going to try to be robust against that. So given a compliance function, the human AI collaborative policy is basically going to be the algorithmic decision if they decide to comply with the algorithm, and it's going to be the human, like the prior human decision that they would have made anyway otherwise, right? So that's a simple model. You can probably generalize this. But we're really thinking about, the human saying, all right, I don't believe this recommendation for whatever reason. So in this case, I'm going to do what I was going to do anyway. In this particular case, I do believe the algorithmic recommendation. So I'm going to comply with the algorithmic policy. So Pi-C is basically just a combination of these two policies, depending on how the compliance function C looks like. Any questions? Great. So before I move on, I want to define what notion of fairness we're talking about. It turns out that pretty much any notion of fairness that we've seen in the literature that's reasonable kind of fits into our framework. But just for simplicity, I'm going to focus on equality of opportunity, which is a very, very popular kind of definition of fairness. And this definition basically says that the probability that someone actually say like gets the loan or gets bail, condition that they were supposed to get it, so like their true Y is actually 1, that's the optimal decision for them, that probability should be equal kind of for both subgroups. So for A equals 0 and A equals 1. So what does this mean? It means that, okay, I'm obviously going to make mistakes because I don't know the true label, right? We're estimating it. But the rate at which I'm making mistakes for people who deserve the loan or deserve bail should be exactly the same across both groups, right? So my false, let me get it right. My false negative rates should be equal, right? And there's an equivalent flip of this definition that says the false positive rates should be equal. And, you can kind of use any kind of definition, but this is the one I'm running with, right? So we're going to define something called the average score for subgroup A. So I'm going to call this pi bar A. And pi bar A basically just marginalizes out the far feature information. So it takes the probability with which a group, a particular individual is going to get the intervention, multiplies it with the probability of that individual having that particular feature vector. The reason we do this is because, it's like if let's say we're thinking about medical procedures, we might see that Black people have, higher blood pressures on average than white people. And so they're more likely to actually need the surgery. And so we want to kind of account for that feature information instead of saying that everyone should get it at equal rates, right? So pi bar A basically captures the score or the need for the intervention for a particular subgroup, given their distribution of features within that group. And we say that pi, a policy, is fair with respect to equality of opportunity if and only if the gap between the two scores for the two groups is equal to 0. So alpha of pi here basically gives us a metric to quantify the level of unfairness for a policy. It should ideally be 0, but we want it to be as small as possible, right? Because that basically says that these two rates are as close as possible. Alpha of pi basically kind of gives us the slack between these two rates, given the different kinds of features we might observe. And with that loss of generality, we're going to assume that the human policy favors group 1 over group 0, right? So imagine that group 1 is kind of the majority population, and they're the ones getting, like the good interventions. And we want to try to lift up group 0. So I'm going to define something called, what is our objective here? So everything I've said here is just setting up notation and talking about, existing definitions of fairness. What we really want is that this algorithmic policy pi A that we're introducing as a decision support tool doesn't reduce fairness regardless of how the end user decides to comply. So again, we have no idea before we deploy a decision support tool how users are going to comply. You can always do a user study, but often people who are in a user study act very differently than the people who are actually going to be the end users. They have a more complex workflow. And so it's generally been very difficult to figure out what kind of compliance pattern they're going to observe until we actually deploy the tool. And by then, a lot of harm has already been done. So we want to understand if we can design an algorithmic policy that kind of comes with a kind of compliance, robust fairness guarantee that it's not going to make things worse in terms of fairness, right? So PI-C, this human AI collaborative policy, we want to say is at least as fair as PI-H. So PI-H was what the human was already doing for any compliance function C. So said alternatively, we say for any C, we have that this alpha of PI-C, which quantifies our unfairness level, is less than or equal to alpha of PI-H. So naturally, you might say, why don't we just say that this policy should be fair? We can't say that it can be fair. Like we can't say that alpha will be equal to 0 because the human always has the option to never comply with the algorithm, in which case they're just going to continue their human policy that they were conducting before. And so the best that we can do is match the fairness of PI-H, like the human policy that they were using before. We can never be fairer than that. But what we really want to do is make sure that we're not more unfair than that human policy, which is kind of what we saw happen in the Virginia sentencing case study, for instance. So again, we're assuming that we know PI-H, but we don't know anything about C. Does this make sense as an objective? Okay, great. Again, feel free to jump in if you have any thoughts or comments. So let me just give you a very intuitive example about how this actually works out. So in this case, basically, we have two subgroups in the x-axis. So we have A equals 0. So imagine that's like your black population, and A equals 1, your white population, for instance. We have pi bar of A on the y-axis. So that's going to be, again, our risk score, our score for each group about how likely they are to get the intervention after marginalizing out their features, right? And here we basically have pi A. This is the algorithmic policy. The algorithmic policy is giving the intervention at similar rates to kind of A equals 0 and A equals 1. So this is a perfectly fair algorithmic policy. And then pi H, pi H is this red line over here, which gives the intervention more often to group 1 rather than to group 0. So again, we mentioned that pi H, we're assuming, is going to favor group 1 a little bit. And so the unfairness of the human policy would basically be this gap, alpha of pi H, right? But the algorithmic policy is actually kind of much nicer to both groups, and it's actually fair as well. So when you release pi A into the world, you might think, oh, pi A is actually a much better policy and it's going to improve fairness. But the problem is that we don't know how humans will comply. So for instance, in this case, humans might decide to comply only for the A equals 1 group. And not comply for the A equals 0 group. Of course, that's an extreme example. But here you can clearly see how the unfairness might actually increase, because then if they were to do that, if pi H were to move here, and this red line remained here, pi C would basically follow this red line here and follow this dashed blue line there. So the unfairness of this overall policy would be this huge gap, which is much larger than the unfairness of the original human policy. So even though we deployed a perfectly fair algorithmic policy here, we see that because of how the humans still selectively complied, we've actually worsened fairness than what they were doing on their own. And that's really the big challenge, right? So that's what we're going to try to mitigate. So here's a simple idea, right? Like, so in this particular case, we had pi A be kind of much higher than pi H for both subgroups. If we were to just move pi A down a little bit, so again, the algorithmic policy is something we design and we have control over, we can stick it to be sandwiched between the two levels of the human policy, right? So in this case, it's between the two red lines. And then you can actually find that there's literally no way the human can selectively comply with the algorithmic policy that increases fairness. So for instance, they can just ignore the algorithmic policy entirely, and then they will continue to have, alpha pi H unfairness. They could follow the algorithmic policy, which is fair, so they will have 0 unfairness. If they were to shift for A equals 1, then you'll see that the gap actually shortens. And if they were to shift up for A equals 0, again, you see that the gap actually becomes smaller. So in this case, like, no matter how they choose to comply, with the algorithmic policy, or whether they choose to comply at all or not comply at all, there's literally no way in which you can actually make the system more unfair than what they were doing before. It's always weakly fairer. And so that's what we're going to call compliance robust, that there's literally no compliance function that would actually cause the alpha of pi c to be worse than the alpha of pi h. Does that make sense?
Can I ask a question on this?
Mhm.
So one thing I didn't quite get in the setup is, can you describe what the human decision maker is seeing? Are they seeing a binary recommendation from the algorithm, or are they seeing this like pi a for that particular subgroup? Because it seems like if they're seeing a binary recommendation for, that person, they could still selectively comply based on whether or not the recommendation's 1 or 0, but maybe not if they're seeing just like this average.
Yeah, that's a great point. So they see pi a, which is the probability with which the algorithm wants to allocate. I think we could round it up to 0 or 1. But then like the rate that they're choosing, the rate that they're choosing with, they're actually decreasing it or they're increasing it. But I think we could round it to 0, 1, which would probably be a little bit more interpretable. And I think the same results would hold.
And then maybe just a quick follow-up on that.
Yeah.
So the compliance function is like, given a pi a, I'm deciding whether or not I want to delegate this case to be decided by the AI, or I want to take it myself, but I'm not like updating my beliefs about the person based on the signal pi a. Is that correct?
Yes, that's a great question. So just to restate it, I guess. So you can imagine multiple ways in which the human reacts to the algorithmic recommendation. So one is that they see the recommendation, they decide whether to comply and follow the algorithmic recommendation, or just do what they were going to do before. Or you might imagine they actually do something much more complicated, where they maybe like average the two or do some sort of complicated updating process and decide to do an entirely different decision, right? And we don't model that. So we're starting with a simple case where they would either default to what they wanted to do before, so they don't trust the algorithm, or they trust the algorithm for this particular individual and they follow that. Given that the decisions are binary, my suspicion is that that wouldn't like matter too much, as long as it's some kind of simple averaging policy. If they're doing some more complicated Bayesian update that's like hard to characterize, I think that would be hard to model.
Okay, thank you.
Of course, great question, thanks. Anyone else that? Okay, great. So in general, before we started this, we didn't even think that it would be possible to design an algorithm that's kind of compliance robust. That seems like you're asking a lot, because you really don't know what the human's going to do, and you're asking for it to like never make fairness worse, right? So the first thing we kind of set about doing is figuring out when you might even be able to make a policy compliance robust. It's clearly not true for kind of all settings, right? For any kind of problem, there are probably problem case settings where you can't create this kind of compliance robustness property that we want. And so this is the first kind of result we have, which is that a policy pi is compliance robustly fair if and only if it satisfies these 3 conditions. So the first condition says that the unfairness of this policy that we're learning has to be less than or equal to the unfairness of the human policy. So that means the human policy has to already be a little bit unfair to give us some slack here. If the human policy is perfectly fair, that actually makes the problem really hard, because the only direction you can go with algorithmic advice is to make things more unfair, because the human's already perfectly fair. This has typically not been an issue in realistic problem settings, because it's very rare that a human policy is perfectly fair. And then second of all, we have to make sure that the human policy, we know that it's going to disfavor group 0 and it's going to favor group 1 more than the policy that we're designing. So this is that sandwiching property I mentioned. So if the human policy doesn't like group 0, then we have to make sure we prefer group 0 a little bit more. And the human policy favors group 1, we have to make sure we kind of, ding group 1 a little bit, right? That's exactly what we saw in this plot. Like, we couldn't set the algorithmic policy all the way up here. We had to basically sandwich it so that it was in between the levels of the human policy. And that sandwiching property is actually what's critical to ensuring that we can have compliance robustness. And basically this makes sure that intuitively, no matter how the human complies, they can only reduce their score for group 1 or increase their score for group 0 without kind of crossing them, right? And the immediate corollary of this, like I was kind of alluding to, is that if the human policy is fair, then the only compliance robustly fair algorithmic policy you can offer is the trivial policy, which is keep doing what you're doing, right? Any algorithmic recommendation we offer them is actually going to, any non-trivial algorithmic recommendation we're going to offer them will have some sort of compliance pattern that will actually make the fairness worse, right? And again, that's partly because a human is already perfectly fair. So the only way that they can really deviate, there's like a very small set of ways in which they can deviate, in which would continue to keep them perfectly fair. Most likely they're going to become unfair in some way or the other. But that's just talking about fairness. We don't deploy these algorithms for fairness. We deploy these algorithms to improve performance, right? In most of these settings, our goal was to say, you know, if we were to build a strong and powerful predictive model, we're able to increase the efficiency of COVID testing. We're able to increase the efficiency of, you know, supply chain health allocation, or we're able to, you know, increase the efficiency of the judge system, court system, and make sure that we give bail to the right individuals, right? So that's typically the first order thing that we care about. But then when we deploy the system, we also want to make sure that it's fair. So in this conversation, I haven't said anything about performance, so let me go back to that. So first, to this end, we want to define some sort of loss function L that basically captures, you know, typically it's going to be mean squared error or something like that. And our optimal policy pi star, so this doesn't care about fairness at all, is just a minimizer of the loss function. So this is just old school supervised learning. This is how we train all our algorithms, right? But again, we haven't said anything about fairness here. So pi star is likely to be unfair, both in the traditional sense and in this compliance robustly fair sense. And we're going to make an assumption that basically constrains this loss function. I'm not going to delve too much into it. I think it's very, very general. And we haven't found a single loss function that kind of doesn't fit into this function, into this assumption. But basically it says that, you know, if a policy deviates from pi star for all inputs, then it should have a higher expected loss. So cross entropy loss, mean squared error, kind of any loss function that you can write down, mean absolute error, like all kind of satisfies this assumption. So just think of it as a general loss function. In this case, we can then write down a very, very simple optimization problem, which is that we want to find a performance maximizing policy pi that is also compliance robustly fair. So when we're training pi naught, we want to minimize this loss function subject to the 3 constraints I showed you that were kind of the if and only if constraints you needed to make sure that a policy pi is compliance robustly fair. So these constraints ensure that it's fair. And this basically allows us to find the, within that class of functions, allows us to find the thing that maximizes performance the most. So sure, you can write this optimization problem down, but like, do we have a solution? Does it, you know, is it actually effective, right? So what we can show is that there does exist a solution in like most cases. So I'm going to define a policy pi b. So pi b basically just tries to check off these constraints that we have over here, right? So pi b basically says for group 0, I'm going to take the max of pi star and pi h, because remember, we want to increase the performance of group 0. And then for group 1, we want to, again, because we want to sandwich it, I'm going to take the minimum of the policy pi star and pi h. So it basically tries to transform pi star in a way that is likely to meet these constraints. And it just kind of tries to check off these boxes. But it may not satisfy the first constraint, right? Our first constraint is that our policy pi has to be less unfair than the human policy. And the reason that, so basically, if pi b happens to satisfy that assumption, then you can trivially say pi b is also compliance robustly fair, and it's performance maximizing. But in general, that might not be true, because we might actually overcorrect for these 2 groups too much. So here we have pi b bar 1 and pi b bar 0, and we have pi h bar 0 and pi h bar 1. So in this case, the gap between 0 and 1, this is the unfairness of the human policy. And the gap between 0 and 1, this is the unfairness of pi b, this new policy that we constructed. And you can actually see it's worse. And that's because we basically helped group 0 too much, and we like worsened group 1 too much, right? And so what you want to do is kind of scale it back towards pi h because you've overcorrected. So if we just squish them back together, you can show that this construction works. We can make sure that alpha of pi b doesn't exceed alpha of pi h. So this is basically kind of how, just giving you some intuition of how you might construct a solution that's performance maximizing, but maintains this compliance, robustness, fairness condition, right? So under most cases, so as long as the human policy isn't perfectly fair, and there actually is a difference between, there's enough of a difference between the human policy and the optimal policy that there's actually room to move these things around, you can actually show that there exists a performance improving, compliance, robustly fair policy if this is kind of holds, right? And this is actually a pretty simple proof. You just kind of use the argument I outlined plus a lot of the intermediate value theorem. Okay, so this is good news. It's showing that we can improve performance, which is what we care about, number one, and in a way that's, robustly fair to how the human decides to comply with the policy. So what about traditional fairness, right? So far we've been not thinking about whether the algorithm is actually fair in isolation, which is what the majority of the literature has been studying. And what we actually find is that these three conditions together might not ever be compatible. So there are lots of problem settings where we cannot achieve compliance, robust fairness, performance improvement, and traditional fairness. So the algorithm that we're designing is actually inherently not fair in isolation, but it does have this nice property that it's fair with respect to the human policy, no matter how they choose to comply, right? So, and the intuition is basically that if the optimal policy pi star is very unfair, and the human policy is kind of close to pi star, then there's no traditionally fair policy that can satisfy our constraints, because we basically have to make sure we overcorrect for these groups in order to make sure that no matter how the human decides to comply, they will actually be fair, right? So if alpha of pi star equals 0, so if the optimal policy itself happens to be perfectly fair, then we can actually get all three conditions. But again, that's very unlikely to be the case in practice, because typically, our data collection is not as rich and as complete for all subgroups. And so typically, your optimal loss minimizing policy will favor the group that has richer, higher quality data, right? So this basically, to sum up, this is basically saying that fairness for human AI collaboration actually looks very different from traditional fairness. And we might not be able to satisfy both of those conditions at the same time. We may need to forego traditional fairness to improve end-to-end outcomes. And my perspective on this is that I don't see why one needs to enforce traditional fairness in human AI collaboration. I don't really care whether the algorithm is fair in isolation, because that's not what's actually affecting end outcomes for actual people. What we really care about is like the composition of the human policy and the algorithmic policy. And so I would argue that compliance robust fairness is what we should be targeting, not traditional fairness. And clearly new algorithms are needed to ensure the fairness of final decisions. I think we've like barely scratched the tip of the glacier for this sort of work. Like you can imagine that, like Alex's question, like you might want to consider more complex compliance functions that people might consider. Another issue that's come up is that, we often have some partial knowledge of the compliance function C. So in the beginning, I made a very strong case that like we don't know anything about the compliance function, but and I think that's true for like a lot of different metrics. But we do know that, in general, judges don't sentence older people more harshly than younger people, for instance, right? And so we have some sort of partial knowledge. Similarly, we know that physicians are more likely to, target high-risk patients across groups and so on. So I think that would really be supported by some sort of empirical analysis of how humans comply with algorithmic recommendations and what the fairness implications are of that. So I think we've seen a couple examples with the radiology study by Agarwal et al., as well as the judge study for Virginia sentencing. But those are all for like a specific algorithmic policy. What we really like to see is how those compliance functions change for different algorithmic policies, so that we can kind of optimize over the class of compliance functions. You might also be able to do some online learning, like with a bandit or reinforcement learning strategy, where you learn the compliance pattern for a specific decision maker over time. So at the end of the day, we're paying a pretty large cost for saying that we have no idea what this compliance function looks like, and we're going to pick the best performance improving policy, but that constraint is very strong. So we might be losing a lot of performative power. If we can actually learn C and tune it to a particular decision maker, then we might be able to do a lot better in terms of performance and increase efficiency. And ultimately, I really believe that at least human decision makers I've worked with, they're not intending to be unfair. These problems are just really hard because we're talking about these very complex conditional probabilities of like, what is your false positive or negative rate for a particular subgroup? You never really observe that in practice as a decision maker. And so it's very hard to actually check off this box of fairness. So you might imagine designing interpretable behavioral nudges that actually improve compliance-induced disparities in a way that the human is able to process them and actually take that into account in their decision-making process, right? So that's sort of where we're hoping to go with this. The paper is on arXiv. It recently came out in ITCS, and you can check out our lab at this website, but love to take any questions or comments or discussion.
Can I ask a quick question, Hamsa?
Yeah, absolutely.
Hi, I'm a marketing faculty at University of Notre Dame. It seems like I mean, I really enjoyed the talk, first of all, but it seems like the idea hinges upon the premise that we can use this class variable as an input to the algorithm, right? So we have to know whether A is 0 or 1, but often cases, these sensitive protected variables are not allowed to be used in the algorithm. So we never know, I mean, we never let the algorithm know whether this is a woman or a man or white or black. Do you
So in
have
most
any feel in
algorithms,
that? Yep.
yeah, this is a great question. So in most algorithmic settings that I've worked with, you actually have to offer that information to the algorithm so that it can de-bias its predictions. I think that's very context specific. But in health, for example, because underserved populations have very incomplete medical records, if we don't leverage that information, the policy we're going to create is almost certainly going to be unfair, right? So we actually explicitly use that information. Cynthia Dwork has like a great article about this back in the day, about how it's actually almost irresponsible to not use the sensitive attribute, and you need to account for it to correct for this. But again, I'm sure it's context specific, but even in algorithmic hiring kind of problems I've worked on now, under the hood, to ensure that the DI metrics are being met, they do account for minority status or gender or disability status, like legally protected attributes.
Exactly. I mean, just give you a one counter example. In the consumer finance market, you cannot use applicant's gender as an input for your decision whatsoever, whether it's a human decision or an algorithmic decision. So in this case, one way to relax those data requirements could be maybe you can build another model to proxy your gender based on all the observables, and maybe that can have some impact on your this was that compliance robustly way of depend.
Yeah, absolutely. I totally agree with you. Yeah. I guess in health, I've often seen it being used, but I totally agree that in other applications, I mean, same with affirmative action and stuff right now, right?
Sure.
But the proxy metric, obviously, yeah, that sounds like the right direction to go. Thank you.
Thank you.
Do I pick someone or
Mohammed? Go for it, Hongi.
Okay. Thanks, Mohammed. And thank you, Hamsa, for the excellent talk. I have a question about, I guess, the optimization problem you set up earlier. So you're optimizing over policies, but did you also say that this is agnostic towards the choice of the loss function? So or should we also be thinking of this as an optimization over the loss functions that we choose?
Oh, sorry. So I was just saying that for the theoretical results, we have a very this works for any loss function, but when you're running this optimization problem, you pick whatever loss function you want. And you actually, we're not optimizing over loss functions. Sorry.
Right, because then there's a trade-off between like the performance, which is vis-a-vis the loss function, and then the fairness that you're sort of achieving.
Absolutely. Right? Yeah, I think that's the cost we pay. So what we're basically saying here is that the performance maximizing policy that we find still has better performance than the human policy. that's what we want, right? We're not going to deploy something that actually does worse than the human policy and then say that, oh, well, it's less unfair, or like it's weakly less unfair than the human policy. That would just be a waste of time. So we're trying to see, can we actually find a solution to this that's, you know, better performing than the human policy and never more unfair than the human policy. But at the end of the day, like that gap, the cost that we're paying is that, you know, maybe we're only a little bit better than the human policy in terms of performance compared to Pi Star, which is maybe like way better, right? And that's why I think the next step to really take this is to try to either learn the compliance function or like restrict the compliance function class in some way, nudge people so that their compliance function class is restricted so that we can like remove that trade-off, right? Or at least mitigate it. I will probably never remove it.
Yeah, because I would imagine that the most interesting thing here is that trade-off also depend a lot on the setting you're using it. Like some cases, you know, a false positive versus a false negative can have very different types of you know, risk trade-offs, I guess. So like it's not always like symmetrical, I guess, of making a decision wrong in one way versus the other way, right?
Right, absolutely. And that's not something that we've looked at. That's a great question, actually. So we're currently applying this empirically to the Virginia court sentencing data, like I mentioned. And there, they only care about, because of equality of opportunity, they only care about the cases where they were supposed to get bail and didn't get bail, right? Like we don't really think so much about the opposite. So like, I think, yeah, that does, I think the loss function that you pick and the fairness definition that you pick also has like huge implications on what this gap is. And I think that's very interesting to study, but usually these are chosen context specifically by the decision maker, right? Based on whatever value function they have for this problem. No, that's a great point.
And are there sort of like attempts right now at your lab or elsewhere to sort of come up with a small scale experiment where you actually implement an algorithm that tries to take this into account? And do people's awareness of an algorithm that is trying to take this into account sort of affect the decision making subsequently?
Yeah, this is a great question. So we've been talking about, so we've run a couple mechanical Turk experiments in the lab to see if we're able to A, understand what this compliance function C actually looks like, and B, understand whether we can actually nudge them to change their behavior. So we'd say something like, hey, we've noticed that you tend to overrule the algorithm when it's, you know, like a Black woman under consideration compared to like a white guy or something, right? And it's, I think for Mechanical Turk, it's easy to change their behavior because they're just trying to maximize their payout, right? Now we're thinking about doing this in collaboration with an algorithmic hiring company to like, for it's like, you know, recruiters are following different policies, like how might we actually, you know, get them to improve on these DEI metrics. And that's much harder because now they actually have a reason and we don't even know what that reason is as to why they're overriding the policy, right? So I would say we're in the very, very early stages, but I'm now convinced that like lab experiments are probably not the right way to go because you need an actual domain expert who has an actual opinion on why they need to be overriding the policy. But if the decision maker doesn't care too much, then it's actually very easy to satisfy this.
Thanks.
Great. So one last quick question before we wrap up. So I noticed that pi h here is not kind of indexed by, for example, a decision maker. How do you think about kind of the role of personalization but also kind of learning across decision makers because data might be scarce? Like how do we structure that problem?
This is an excellent question. So in this case, like we're thinking of pi h as like an individual decision maker, right? Like Mohammed, you're making these choices. If we're thinking about this as pi h as like a population level of decision makers, I think this still applies. We would just say that for a particular decision maker, it may be more or less unfair, but as a population of decision makers, it'll be compliance robustly fair. But absolutely, I think this is where, I mean, decision makers, you know, they leave and then new decision makers enter, right? We sometimes have this cold start problem. So I think this is where the like online learning problem of actually learning the human decision makers policy and learning their compliance pattern is really critical. So I would think of this as a population level at this point, where like for like judges, for example, you do have like a pretty long historical record, but like recruiting, you know, people come and go, right? So I think that's an excellent direction. Like I said, I think this is just highlighting the problem and saying there's something we can do, I am very excited. I think there's so many directions that this could go in that I'd be very excited to see.
Awesome. Well, I think we're at about time. So on behalf of the IDE, I'd like to thank you, Hamsa, and also everyone who was able to join us today.